Hello everyone, and thank you for giving me this opportunity to present my research as part of the workshop on challenges and promises of inferring emotion from images and video in conjunction with CVPR 2020. The title of my research is Discriminant Distribution-Agnostic Laws for Facial Expression Recognition in the Wild. In this talk, I will cover an introduction on problem statement, our contribution, our proposed method, the preliminary concepts that are related to our work, our proposed loss function, and how to optimize it. And in the experiment section, we will experiment with a wild toy dataset, and two widely popular facial expression recognition datasets called AffectNet and RAF-DB. And I will finally conclude this talk. Facial expression recognition is actually a multi-class image classification problem where the input space is a 2D facial image and the output space is a label that we assign to that input from a fixed set of categories, such as neutral, happy, sad, surprise, anger, disgust, and fear. So for this K-class image classification problem, K is actually 7. Here you see some sample images that we have assigned some labels to from the previously mentioned labels in the previous slide. Facial expression recognition has applications in healthcare, autonomous driving, human-computer interaction, and education. For facial expression recognition, we typically deal with two types of dataset. One type of dataset is lab-controlled datasets, such as the Japanese female facial expression dataset that you see here. It has a small number of samples, number of subjects, and inter-class variation, and because of this, they are not suitable for real-world applications. On the other hand, we have natural wide datasets, such as AffectNet, that has large number of images, large number of subjects, large inter-class variation, and inter-class similarity. And because they are larger scale and they're acquired in an unconstrained environment, they are suitable for real-world applications. Because of the state-of-the-art result on visual recognition task, we also use a convolutional neural network-based approach for our method. So in particular, CNN extracts spatial features from the input image, and the deep features are pulled into the embedding space using a feature pooling layer. Finally, a softmax function as a loss function will yield a prediction for the input. However, there are some challenges when working with wildfire datasets. There is large interclass variation, meaning that the images from the same class are very varied. And there is also large interclass similarity, meaning that the images from different classes might be very similar. There is also extreme class imbalance, meaning that the dataset is divided into majority classes and minority classes. So our goal is to map from the input space to a well-clustered feature space and achieve optimal inter-class compactness and inter-class separation. Softmax loss that is typically used in a convolutional neural network, however, is insufficient for discriminant features. So center loss comes to the rescue and it minimizes intra-class variation, and because of this minimization, it actually implicitly maximizes inter-class separation. However, looking at the deep features learned by center loss under wild scenarios, we can see that even though majority classes are well separated, but still minority classes are overlapped in the d-dimensional embedding space. So our solution is discriminant distribution-agnostic loss, or DDA loss for short, to regulate deep features in the embedding space where extreme class imbalance exists. DDA loss yields discriminant features for wild scenarios. It minimizes inter-class variation and it maximizes inter-class separation for both majority and minority classes. It is jointly optimized with softmax loss and center loss. Here we see how DDA loss is compared to center loss when optimizing an embedding space. As you can see, center loss is pulling the deep features of a class toward their corresponding class center in the embedding space. But DDA loss is not only doing that, but also pushing the deep features of a class away from other class centers. So as a result, we will have a more optimized embedding space in the case of DDA loss, where both majority classes and minority classes are well separated. So to summarize our contribution, we propose a novel loss function called discriminant distribution-agnostic loss to regulate the distribution of deep features in a d-dimensional embedding space, where imbalanced distribution of data exists. DDA loss implicitly minimizes inter-class variation and maximizes inter-class separation for both majority and minority classes. We show that DDA loss can be optimized using the standard stochastic gradient descent algorithm. DDA loss can be promptly applied to any deep neural network architecture with minimal intervention. We conduct extensive experiments on a synthesized wild dataset and two popular larger-scale wildfire datasets called AffectNet and RAF-DB to demonstrate the improved recognition results with the proposed method. Before we dive into the proposed method, let's review some preliminary concepts that are related to our work. So in a CNN-based recognition system, the input is a training batch of M samples containing the input image and its associated label. Then CNN extracts special features, and the d-dimensional deep features are pulled using a pooling layer. Then this d-dimensional deep feature is fed to the last fully connected layer to extract raw scores for all the classes or logits. And then a softmax function will calculate normalized scores for that input image to yield a prediction. Finally, the cross entropy loss will calculate the discrepancy between the prediction and the true label. Softmax loss is actually the combination of the last fully connected layer, the softmax function, and the cross entropy loss, and it's formulated as below. Let's see how center loss works. Center loss minimizes the inter-class variation by penalizing the distance between the deep feature and its corresponding class center in the embedding space, and it's jointly optimized with softmax loss, where the hyperparameter lambda is controlling the contribution of center loss to the total loss. On the left side, you see how data flows in a supervised learning algorithm jointly supervised by softmax loss and center loss. In this slide, we see the effect of softmax loss and center loss on a normal actual dataset called MNIST, which is very balanced. As you can see, we are not achieving a very good discrimination with softmax loss, but center loss, on the other hand, is creating compact clusters that are well separated from each other. But when things get a little bit messier and we are dealing with a wide dataset, you can see that even center loss is struggling, and we have minority classes overlapping in the embedding space. So our solution, discriminant distribution-agnostic loss, properly separates cluster deep feature vectors for both minority and majority classes in the embedding space. And it's formulated as below. DDA loss estimates the probability of deep feature xi belonging to cluster K with center Ck using a softmax function. Minimizing DDA loss is actually maximizing the log likelihood of this probability over a batch of M samples. It pushes the deep feature xi from the classes that it doesn't belong to, and it pulls the deep feature toward its corresponding class center in the embedding space. This is how data flows in a learning algorithm that is supervised jointly by softmax loss, center loss, and DDA loss. As you can see, for center loss, we are only inputting the corresponding class center for the deep features, but in DDA loss, all class centers are employed. Intuitively, the contribution from both majority and minority classes are taken into account to create a distribution-agnostic loss to mitigate the bias toward majority classes. The proposed DDA loss, as mentioned, is jointly optimized with softmax loss, center loss to create the total loss, and the contribution of center loss is controlled by the hyperparameter lambda, and the contribution of DDA loss is controlled by the hyperparameter gamma. Let's dive in how to optimize the DDA loss. The proposed DDA loss is differentiable and can be optimized with the standard stochastic gradient descent algorithm. The joint optimization of DDA loss with softmax loss and center loss will contribute to their gradients with respect to the deep features and centers. This is how we calculate the gradient of DDA loss with respect to the deep features. Intuitively, this optimization will distribute deep features in the embedded space so that it minimizes DDA loss and the total loss. And this is how we calculate the gradients of DDA loss with respect to the centers. Centers are randomly initialized according to the heat initialization method, and we use this update formula for updating the centers. We summarize the training of a supervised learning algorithm such as CNN with DDA loss. We initialize the network parameters and centers. We sample a mini batch of size M from the dataset. We forward pass all samples in the mini batch and we calculate the loss function, which is the joint supervision of softmax loss, center loss, and DDA loss. We calculate gradients with respect to the deep features and the centers, and we update the network parameters and centers. We repeat steps 2, 3, 4, 5, 6 until convergence. Experiments. To mimic the characteristic of a wide dataset and visually and intuitively analyze our method, we create a wild MNIST or WMNIST by randomly sampling from the original MNIST dataset. Few classes in the WMNIST have drastically low number of data points, such as class 4, class 5, and class 7. To visualize these 2D deep features, we use a deeper version of the LeNet network called LeNIST++, and we use a 2 neuron fully connected layer right before the 10 neuron fully connected layer in the end, and probe it for visualization. Here's the result of our visual experiments on the WMNIST dataset. As you can see, center loss, as mentioned before, has overlapping regions for the minority classes, but on the case of DDA loss, as we are increasing the contribution of DDA loss by increasing the gamma parameter, we are seeing that both majority classes and minority classes are being separated in the embedding space. Quantitative analysis on WMNIST. We train LeNet++ on WMNIST and report the classification accuracy on MNIST tested. As you can see, DDA loss with gamma parameter set as 7 is achieving an accuracy of 97.34%, outperforming our baseline methods, which is softmax loss and center loss. For our wild experiment dataset, we first experiment with AffectNet, the largest wild FAIR dataset available with 280,000 training images and 3,500 testing images. The input size is 224 by 224. We do data augmentation on the fly, and we use the CNN architecture ResNet 18. We train ResNet 18 on AffectNet for 20 epochs with batch size 128, and the initial learning rate is 0.01, decayed by a factor of 10 every 5 epochs. This is the comparison of various methods on AffectNet. As you can see, DDA loss with gamma set as 4 is achieving an accuracy of 62.34%, outperforming other state-of-the-art methods and our baseline methods. This is the confusion matrices for AffectNet. As you can see, center loss is boosting the recognition accuracy for most of the majority classes, but is degrading the performance for minority classes. On the other hand, DDA loss is boosting the recognition rates for the minority classes and is keeping comparable result for majority classes. For RAF-DB, we have 12,000 training images and about 3,000 testing images. The input size is 90 by 90, and we do data augmentation on the fly. CNN architecture is ResNet 18, and we train it for 60 epochs with batch size of 64. Initial learning rate is 0.01, decayed by a factor of 10 every 20 epochs. Here's the comparison of various methods on RAF-DB. As you can see, DDA loss again with gamma parameters set as 5 is achieving an accuracy of 86.90. Because the RAF-DB's testing set is imbalanced, we also report the average accuracy, which is actually the mean of diagonal values on the confusion matrices. DDA loss with gamma 5 is achieving an average accuracy of 79.71%, outperforming other state-of-the-art methods and our baseline methods. Here are the confusion matrices. Similar thing happens on RAF-DB compared to AffectNet, boosting the minority recognition results and keeping comparative result for majority classes. As you can see, as we are increasing the contribution of DDA loss, we are achieving higher accuracy, but after a certain point, the accuracy is decreasing on both RAF-DB and AffectNet, which means that DDA loss has to be optimized in a sweet spot. Here are some example recognition results for both RAF-DB and AffectNet. On top row of each dataset, we have correctly classified images, and on the bottom row, we have misclassified images. So to conclude, we propose discriminant distribution-agnostic law for facial expression recognition in the wild. DDA loss implicitly pushes deep features of a class away from other classes and pulls them toward their corresponding class centers in the embedding space. Supervised jointly by softmax loss and center loss, differentiable and can be trained using SGD. Any state-of-the-art CNN architecture can promptly employ DDA loss, and our experiments with a toy dataset and 2 wildfire datasets demonstrate the superior performance of DDA loss under wild scenario. Thank you for listening, and here are the references.